Right here is the right here. So I'm going to bring this a little smaller. So this one, stress ratio factor versus allowable with and without concrete shoulders. Okay, right here. First number was 36 kips. Check your first row. Okay. Stress ratio factor was 0.306, I think. Something like that. 0.317. 0.317. So I go from here, draw a line, and come to allowable repetition was close to 200 something. Check your table. What is the number then? Allowable? Yes. 27,000. Yeah. So 27, right, between that, correct? Does that make sense? So that is around 27,000, 30,000, close to that. Everybody with me so far? So you have to do every row, you will have to find the right load. Stress ratio factor remains the same. So you are basically pivoting almost like this. You're going like this, like this, like this, like this, right? As the load goes up, number of allowable repetitions go down. On the other way, if you go like this, it will go up like this. If you go outside the chart, just call it infinite, right? If it goes too high, just call it infinite. Does that make sense? Unlimited. Unlimited, right? So that's what you have for the allowable repetition for each of these conditions. Now there is a similar number for tandem, the same chart, except that the tandem loads are on the right hand side. That's all. Same thing. So you pick the right load for the tandem and do the same pattern. Same pattern. Got it? It's the same equation that I presented. It's the same equation. Sigma over SC is stress ratio factor, if you remember. From this that we get allowable repetition. That's how you get your allowable repetition, right? Everybody with me so far? Everybody online? Okay. Can this can see this very clearly? Yes. Yeah. Oh yes. Yes. Now, the same thing you have to do with the erosion factor. So same logic is applied for the erosion factor. You have single load right here, erosion factor and allowable repetition. For fatigue and erosion, you do the same thing, different charts. Got it? Using the models I just explained earlier. Now let's go back to the table. Right here. Now I'm at the table. So this still brings everything together. Right here, for the single axle, I use my table 601027,000, 64 1.2 million, and then after a while it becomes unlimited. Got it? Same thing here, it becomes unlimited. Right? So you do it for single axle, you do it for tandem axle. Same logic. But remember, the stress factor has changed. Remember the two numbers. Erosion factor has changed for tandem axle, right? Now you add them up. Each of them independently must be less than 100. Both are happening at the same time, right? Both of them independently have to be less than 100. So 62.8 and 38.9 is a little conservative. It's not close to 90, so 9.5. If this both were around 20 damage, then it is very conservative. So I can still afford to drop my thickness to 9 inches. I can try to make them closer to 100 to make it a little realistic. Otherwise, it's a conservative design. Can everybody understand that? It's a trial and error process. Because all my deflection, all my stresses depend on the thickness. So I need to get it.
Summation of these two values or only one value?
Each value.
Each value we have.
Yeah, this is part. If I add these two up, they are more than 100. Correct? So this would have failed. But this has passed. Each of them individually have to be less than 100. So 62.8, I can bump up a little bit, right? So I can drop my thickness and save money and make it 9 inches and drop. Does that make sense? And this will also work, but not that, right? And you can imagine the failure, the damage percentage is obviously for erosion is going to be less than the actual drop. Everybody with me so far? Question? But this is the mechanistic empirical design for PCA. Questions about that? Let me go through the slide, see if I can. So right here, this is a nice review now that I've covered this. So it accounts for modulus of reaction, modulus of subgrade reaction and MOR, and axial load spectrum. Then I just explained this 50 to 170 to 230, that you have to account for the base and stabilized phase. Okay. You have to get the design E-cells if you're getting only 18 chip E-cells, right? This is the same thing in distribution factor. Yes, so right here. Choose a trial slab thickness, and you determine the Ni for fatigue failure, and you determine Ni for erosion failure. If fatigue and erosion, you have to add for fatigue and erosion, both of them, and both of them individually should be less than 100. Okay, if the sums are less than 1, your design is good, do not increase the slab thickness. So this is your design volume. Experience. Start from experience. That's somewhere you start. So if your state is used to 8 inches, it's tendency to start from there, right? Or typically 6 to 8 inches work for my state. You start from that number, right? So right here, if you had access to the table, I would have made you do this 11 million trucks. If there's 11 million coming, this is the same charts I've gone through. I've given each of those. Oh yeah, it's explaining each of those sections. If you have access to this particular chart, we could do one problem of just one row. If you want to try, I can keep it open. But you have access to it. Do you have access to this notes? You have access to them because I want you to plug it in. So right here you have K of 100, and you have a PCA design of JPCP with asphalt shoulders, no concrete shoulder. Design life is 20 years. Okay, so if you want to take a photo of this, right, for this condition, right, and if I give you one row, just one row, right, let's say 11 million E-cells, right, that means you don't have to do the whole thing, just one row, not even tandem, only single. You want to try, I'll open up the sheet and you can try. You want to try that? You can try it. You have access to it on the phone. So you have access to the sheets. Yeah. Do you have it, access to it? Yes. If you have access to it, then you can do it. Otherwise, we can move on to another one. Anybody online would like to try? There's a chat somewhere. No. Use this.
Would you expect good presentation, Professor?
What? Good presentation? This way? Is that what you're looking for? It's not coming here.
No.
Now it's good?
Okay, now okay.
Okay, perfect. So right here, you can try this for clay subgrade, 100 pounds per cubic inch, 4-inch untreated subbase. Concrete MOR is 650 psi. Covered, no concrete shoulders, right? And then, so you have K of 130 PCI from the table. So you have to convert from 100 to 4 inches of untreated base, and that's your sheet right there, right? You will have to use this, okay? And you will have to plug in the same thing. That's almost the same example as the textbook as it explained. And you have your stress factor, and then you connect the two. Right here, that's for different. I wanted to do a problem for, but let's do the actual design. I think it's going to be hard to do a problem. Okay. I will do the actual design next. So this was the PCA. Any question about the PCA, which is the mechanistic empirical? Now I will go into the astro design. This is for rigid, right? I'm going to, if I can capture all the input parameters here. For the view postman as well. All right, let's do this. All right, now we're going to go to the last method of the payment design. That's the fully empirical astro payment design. All right, let's go. All right, astro method. We're going to go through this in detail. First couple of things. We are going to go through all the input parameters. Right. Design life. It's whatever that is, and that relates to design instance. What changes when I calculate ESUBs for concrete versus I calculate ESUBs for asphalt? What changes? What changes? I covered that in my graphic. What factor changes? EALF, equivalent axle load factor for concrete, is completely different than for asphalt and concrete. So my truck factor is going to be, so ESUB calculations, the calculations are the same, but the factors are different. So you have to use EALF of concrete structures, which is going to be completely different, right? Concrete payments instead of asphalt, right? That's number one. Okay. Next, let's keep going. There are lots of parameters in this, lots of exciting parameters. All right. We make this bigger. There it is, very good. All right. Couple of things I'm going to explain as I go through this. This is couple of important information. One, modulus of elasticity of concrete. That's right there, E of PCC. Okay. Effective modulus of subgrade reaction. So effective, and that's a very big process. I'll come back to it in a little bit. K value, K effective. Okay, next. MOR, modulus of rupture, or SC, that's a concrete flexible strength. Then load transfer coefficient, J. That depends on whether you have shoulder, yes or no, right? Tie bars, yes or no, right? Asphalt shoulders, asphalt or concrete, something like that, right? So this is looking at all the kind of coefficient, load transfer coefficient. Okay, so of course, the better the load transfer, lesser the stresses. Next, drainage coefficient is same. Drainage coefficient is D. That's looking at the drainage. Okay. And then the match line. And then keep going down. Oops. It's very sensitive. Right there. You can look at this. This equation is so big that it needs 2 tables, 2 pages for the turn line. Match, yeah.
Next line finally.
Yeah, match line from the top comes down. Then you have your delta PSI. Same concept as the other one. Okay. So the match line and solving this is easy. I want you to understand every parameter and how it impacts the design line. Next, your design thickness you don't know yet. You are trying to find. Okay? Right? So you will come up to this point. You will draw a straight line. That's it. Stop right there. Then you go down. Start from the other side. Then you have reliability. We covered this in before. So you can have higher the reliability and higher the thickness, right? Then you have standard deviation, and that is typically 0.35 for concrete. That's right there, 0.3 or 0.35. And then you have easels. Got it? Design easels, where is it? Right here. And then you meet up where they intersect. Where this and this intersects, that's the thickness. Got it? Everybody got? That's your design. But now I'm going to cover each of those parameters in excruciating detail. Right? Everybody with me so far? Got it? So you got all the parameters that involved. Design life, design itself, modulus of elasticity, modulus of substrate reaction, K effective, MOR, SC, load transfer, drainage coefficient, and all of those. Okay, let's go. Any questions online as you go through the design methodology? Let's look at each of those parameters. Now, first step. This is the 4-step process of getting the modulus of subgrade reaction. Not one, but several. Right here, let's look at this. First thing, estimating the subgrade reaction. Okay. You start with the soil, right? Subgrade reaction. Okay. And you have your subbase thickness. Okay. So you start here, right here. If your subbase thickness is 6 inches, you go up and you go down. You have your subbase modulus given to you. In this case, it is close to 30,000 psi. Okay, that's this number right there. And then you have subgrade modulus given to you, 7,000 psi. I think.
Yes,
7,000 psi, right? It's testing mindset, right? Right? And then you go right and come back up on the turning line. Yes. And you get the composite modulus of 300, close to almost 400 PCI for infinite subgrade. For infinite subgrade. You got it? You're not done yet. You got a couple more steps. That's first of 3 charts. Okay, that means it accounts for subgrade modulus, thickness of the subbase, subbase modulus, and if that soil was infinite, my starting point is 400. Can I move on? Everybody understood that? Next. Keep going. Now that I started off with that being a shallow depth, infinite depth, you might have a solid rock in a few feet from this pavement, a rigid foundation. That means it will give better support than you designed for. All right. So right here, modulus of subgrade reaction, assuming infinite depth. That's from the previous chart. Okay. And if that was and modulus of so let's say your if roadbed solid residence modulus was a certain number, right here you bring it up. Depth to rigid foundation is 5 feet. That means my rigid foundation is not infinite. It is only 5 feet. Right there, you come to the right, you pick the number from the previous chart, come down and look at the number went up. From 210 or 210, it became close to 350. Because the rigid foundation is much closer to the pavement than you had anticipated. Does that make sense? That's the chart number 2. One more chart. Can I move on? So, right. So, what I ask my students is not how to read the chart. What are the factors my subgrade reaction depends on? They should understand what factors they are. Depth of subbase, modulus, development, all those factors, because that is what will make them think what impacts is that. Okay, now next one. Okay. All right, keep going. Let's we are got the nomograph. This is the second one. That's the next one. I need to be focused. All right, this is what we got. Last one. All right, this is the last chart, third chart of the modulus of reaction. After the first 2 charts, you will get a single number right here. Okay. Then there is a number called loss of support. That is how erosive your soil is. If your soil is very erosive, you have a loss of support of 3. If your soil is not erosive, you have loss of support of 0. Does that make sense? So if it is it is not erosive, it will be on the equality line. There will be no reduction. If your loss of support in this case is 1, from 540 it became 170. So just by having loss of support 1, it dropped by 300 times, right? So it kind of really dropped the reaction. That's your final number corrected and the modulus of subgrade reaction. That's your effective modulus of subgrade reaction after 3 charts. Modulus of concrete, I want to go through these again. This is very important. If I do not measure this in the lab, it is given by 57,000 square root of FC prime, right? And you can use that comprehensive strength, it's easy to measure. Right, your loss of support. Remember that last cable? So between cement treated base to fine grain, so you will have 2 to 3 and 0 to 1. Can you imagine? So you will have to use based on what your base is, you will have to use this loss of support. But it really punishes you if it's anything that is loses support with water. Right. Next, load transfer coefficient J. That's the one I explained to you somewhere here. Load transfer coefficient J. Right? depends on the load transfer device's tight shoulder, and then you have a drainage coefficient as well. Let's go through each of those tables. Right here. Table 12.19 is the J number right here that you use in the first table, right? Look at this very carefully. JPCP, JRCP, asphalt shoulder, yes. CRCP 2.9, tight PC 2.5, 3.1. So the way this number is working is that the higher the number, the poorer the load transfer. Just the way the equation turned out to be. Does that make sense to you? So in this case, you like 2.9 to 3.2, low CRCP is very tight, one of the best. And you have very low load transfer coefficient, right? And then 3.8 to 4.4 is asphalt type of shoulder, no shoulder at all. So in this particular equation, J turns out to be in the denominator, right, so to speak. So that's why the higher number is not good. Next, ooh, just did that. Right here. Drainage coefficient, I'm close. Right here. Right here. Same thing as the M value. This is exactly same as the M value. You want the material that drains well. Right here, this is almost same as the M value. So if you have excellent drainage, 2 hours versus greater than 0.5, 0.7. So same concept as PD as well. All right. So they did a very nice comparison of between ASHTO and PCA. So comparison figures between ASHTO and PCA. If you are looking at your ASHTO ESAs is 1.2 million, it gave you a PCA thickness, slab thickness of 5, right? For ASHTO, it gave you 7.5 for no concrete shoulder. So they did a comparative analysis between the PCA and ASHTO. So 5 to 7.5, 9 to 8.3. So it goes different ways in terms of how the design was. So this is both my designs. I want to do the tutorial and I have some very fun questions that I want to discuss. So any questions for me as far as the two design goes? I want to pose some questions to you guys because I have it with me and see if you can answer it for me.
Is there any software developed to find out the objective survey?
Absolutely. This is all software has been done, vetted. Now, all of this is done, at least in the US, by consulting firms, right? And time is money, right? So they want this done efficiently, and they just crank out designs left and right? They have only finite number of conditions they will see. So all the payment designs are done by consulting firms. So, pardon?
By manual calculation.
No, by software. Completely by software. Hmm? They have a ASHTO where I think Darwin or something like that. And see, my job is not to teach software to my students. I'm against it. I want to teach them the concepts. In real life, they will go ahead and use the software. My only worry is if you don't understand what goes in the software, they have a problem. So the industry folks get upset at me that I don't use software, but I know they want efficiency, right? They want efficiency, they want throughput, right? I get it. But for me, it's important that my students understand what goes into the software. We have different. I'm going to open up the tutorials, but I have some other questions. Any questions online for me?
Okay.
Okay. Questions as well. We covered a lot of ground today, I think. All right, you want to try this? Right here, let's look at these. What type of testing is performed? Let's look at this right from the beginning. Some of them are in bold already. I think we are. The reason this happened in bold is because I made the solutions first, then I made the problems. I left the solution. So that's what. But you guys make do it. Right here, so Poisson's ratio of concrete, and then you have dowel joints, right? Then this one, easels is given to you. Right here, so this is very critical. What is the most common problem with way more is deflection cracks on overlays, right? And then let me increase the size a bit. All right, let's go to this typical design life. You have around 25, 30. Purpose of the payment, input parameters that's given to you, doing the base. Let's go down a little bit. Okay, for arterials, it's given to you no curling. So if there are no curling stresses, if the temperature is constant, that is correct. Substrate modulus on ASHTO depends on the damage. We calculate the damage equation that's given to you. What is the surface permeability value? That was 0.5, it was in the slide. Let's look at this. Expand joints are required in rigid pavements. True or false? No, sir. Yeah, you need a construction joint, right? Unless you're pre-stressed. So the true or false, right? So you guys can let's go through this a little bit online. Let's do this together.
Construction construction
All right, let's flexible pavement has low flexural strength. False. Okay. Load in asphalt format is not transferred by subsequent layers. False. It transferred through what? In asphalt. Grain to grain load transfer, correct? Thermal stress analysis is required in concrete pavements. For reinforcement, right? And for design, we saw there was no temperature in design, only erosion and that. Rutting is a non-wheel path surface depression. Alligator cracking is related to the poor drainage of substrate failure. Could be, right? If it became weak, you will have cracked, tensile strains go up, right? So if you have a very weak substrate, right, you could have that, right? Tensile strains could go up and you could have. Ravening is caused by poor compaction, not enough binder in the mix. Yeah, it's a construction issue, right? I say the mix is cold, not done, you have spots of that. Reducing modulus of coils decreases as the applied deviatoric stress increases. Remember, it's a cohesive soil. So, cohesive soil is shear failure. Based on the Morse circle, shear stress is half of the deviatoric stress. So, this is correct. For completely cohesive, as you increase the deviatoric stress, Your shear stress goes up, you will have a shear failure, and that's what you have. Stress invariant is directly related to level of confinement in the soil. Therefore, the residue modulus increases as the stress gradient increases. True or false? What is stress invariant? What is stress invariant? Sigma x plus sigma y plus sigma c or sigma, all three regions. If I'm doing a triaxial test, it will be 3 sigma c plus sigma d. So yes, it is very much related to that. But this is a trick question. Therefore, the resident modulus increases as the stress gradient increases. This is typically I would ask, but this is only if it's a completely granular soil. That is the case. If it's a cohesive soil, the previous one dictates. So then I ask these kind of questions to my students, and they are like, they get every sentence, they understand the depth of knowledge. Lower the percentile value of resonance for higher traffic level. Do you remember this? We covered this yesterday for asphalt institute. If 87.5% values are lower, or versus 60%, so it's so you have backwards, right? So if 87.5% values are lower, then you spit out a very low values, right? Compared to then it's false. It's exactly that. They're very tricky. So like you need to have a complete command of the subject matter to be able to answer. So as I told you earlier, rarely my quizzes have any math in them. You know, so it's just completely this part of stuff. You guys don't have the software when you go through it. Can you guys really do this quick one? There should be a very quick calculation. Design lanes, have you already did this in the class, right? Alright, this is clearly getting the truck factors. Remember the amount of trucks weighed, right? And we get that. So let's look at this. I'll explain this problem, right? So here you're using a loadometer station data. That means to get truck factor, you have to weigh the trucks, not count them, weigh them, right? Look at this down. Number of axles weighed is here, and we go down, all the way down, and number of trucks counted and number of axles weighed. So you have to look at the number of axles weighed. Counted is not enough. So you have to do the math to get the truck factor for each of them. 3-axle truck, 4-axle truck, and then 5-axle truck. Using the same math. Remember you got 1.38? I did that in the class. You have to do the same math here. Okay, another true or false. Please answer one by one. You start from the top or from the bottom. Remember structural number A1, D1, A2, D2, A3, D3. You from the top because that's the only unique solution, and then work your way down. Eventually, you are right. You are protecting the subgrade, but you start from the top. So that's the false, right? Just get it?
Yes.
Everybody got that right? The structural number required increases with traffic and resident modulus of the supporting layer. Think and tell me. Structural number required to protect that layer. No, sir, false. वो decrease होता है. हाँ? Sir, MRP value बढ़ती है तो structural number correct. Correct. So your and is the trick. Traffic से increase हो रहा है, पर resident modulus से decrease हो रहा है. Right? So you have really have the command of the subject matter. So if you just go with the traffic increase, you think, oh yeah. But then there's an and there. So you have to know that no. But if I had kept or something like that, then there will be a different one. Here I'm saying and. Okay. Structural coefficients depend on the structural number and the thickness of the layer.
Yeah.
False or true? Think and tell me. Yeah. Thickness पर तो depend करता है. So if structural number, let me look at this. Structural number is A times D, correct? Times N, right? But does it really mean that I calculate A with this What is A dependent on? What is A dependent on? Structural coefficients. Modulus, absolutely. A is dependent on modulus, right? That's a trick. So you fall in this trap. Oh, I understood the equation. So A is equal to SL divided by no. This is independently observed, right? So you are correct. A is dependent only on the modulus of the material. So that's a false. So that's around 20 push-ups. Right here. ELF of 35 chip distance is 12.5. One causes 12.5 times the damage. Is that true or false? Anybody online here? Can you see? Which one is worse? 35 chip single axle or 18 chip? Oh. Which one is worse? Which one is heavier? Anybody online? Yeah, 35 chip is heavier, right? It is going to cause more damage. Yeah, 35 chip will cause 12.5 times more. Thank you so much. So that you should have got right away in a few seconds. Right. Next one. Astro flexible pavement design is mechanistic empirical. True or false? False. False. It's fully empirical. Asphalt Institute is mechanistic empirical. Reliability of problem design is not incorporated in the AI method. Yes. True or false? It's a trick question. It is not directly accounted for like the R value, but it is accounted for in the subgrade percentile value. Correct? So that's a false. It is accounted for. Just talk about percentile value, right? So if it's heavier traffic, I will push a lower subgrade value. That's reliability. I'm just reducing my risk. Does that make sense? Okay, next one. AI does not account for any seasonal effects at all in the design. True or false? False. Yeah, it does account for seasonal effects. We talked about that. On the annual level as well as. Yeah. All right, let's look at this. This is the fun one. I guess you all have to try this, okay? Think and tell me. List and explain how each of these design inputs will impact the overall thickness, assuming everything else is a constant. You understand the question? So if I increase the traffic, everything else being constant, will my thickness go up or down? That's my simple question.
It will increase.
It will increase, right? And if traffic goes down, traffic goes up, thickness will increase. Subgrade strength. Strength goes up, so that my thickness will go down because I got better support. Resilient modulus increase. Effective load bed modulus. Astro. If my stiffness increases, my thickness drops or increases? Will drop, right? I got better support. Reliability. If I go from 90% to 95%, 90%. Increase. You have less failure. If I go from 90 to 95 to 99%, that means I'm taking less risk. I want only 1% chance. Right? So I'm going to bump up the things. From 10% failure, I want only 1% failure. What will I do? Bump up the thickness. I will pay the price somewhere or the other. Change in serviceability. So I go from delta PSI from 5 to 2.5, and then instead of that 5 to 3. Yeah, you are making them go longer, so you will have a greater thing. Correct. This is a very good one. This exercise is very good. Everybody okay online? All right, let's look at this. All right. How are long-term and short-term seasonal accounted for in Astro design? We have covered this. How is short-term and long-term? Let's start with short-term first. Or long-term first.
Long-term तो 0.8 कुछ करके.
Delta PSI for frost peeve and swelling. Long-term. Remember, I explained to you that in the certain Astro road test, they had blocked off traffic. Right? A certain section of non-straight portion, they had blocked off traffic. They didn't want to traffic it because of fear. They said, okay, I'm going to evaluate frost peeve and swelling. Does that make sense? Then how do they account for short term? Anybody online here? Remember I gave you the 12th, January, February, March, April, and you calculated the what did you say? You calculate the damage. Then you average the damage and you back calculate what that modulus would be. Remember how you got 2200 psi? So that's how you account for short-term seasonal factor. Right? Everybody with me so far? You remember the table? Yes, online, everybody with me? Next one. What is ELF? Let's get this right. We did this a lot yesterday. Equivalent axle load factor.
The contact pressure. Factor which is
What is it?
Category vehicle will convert it.
Number of repetitions of what? XY divided number of repetitions of 18 axles, right? So ELF is number of repetitions of X yes, divided by N18. And N18, 18 chip single axle load. And if it's 1, that means they're exactly the same. That's ELF, right? Remember, that's the only definition. What are the factors that affect ELF?
Axle configuration, somebody says.
Yes, tandem versus single, that is correct. What else?
we don't with the A with totally.
Load is one, go ahead.
A with totally.
Axle load, absolutely. Axle load, what else? What else? What else? I talked about condition of the pavement. New thickness of the pavement. New pavement versus old pavement. So I hit you guys hard. And I just explained about concrete versus asphalt. Very thick was ELF will change. So I asked for these three main factors, but there are many factors. But you have to clearly understand why, right? It's the ratio. And those are the very fundamentals of pavements, right? And then everything. Next one. How do ASHTO design account for conditions different than the ASHTO road test? I have said this multiple times. Remember, you are extrapolating from this very, very limited data. You are designing 50, 60 years later. How are they accounting for factors outside the ASHTO road test?
So we increase.
You're there, you're close. You increase the thickness, but on what? You're applying factor of safety through reliability, through S0, standard deviation, but minimum thickness requirements, right? All of those are fictitiously increasing not fictitiously, they're just increasing the thickness because you are outside the database of this. But go ahead.
We increase that grass.
Which one?
So when we
Okay, it's fine.
Sir, because in the lab test we have in that the lab test, sir, when the grass touches there and we increase that grass little.
Oh yeah, remove this out. Yeah. You're looking at the AI method. Yeah. So you're trying to match that. That's correct. Use the active to determine the lowest initial cost, and that is the cost question that I said. I'm going to explain this problem. I did this in my class, but look at this. This is the one I was saying as a project. Try it if you have time. So this is the problem I give, right? 250,000. They have to be 50 inches, right? And then you have 7 stabilized bays. Cost is given to you, and they can use at least 3 scenarios with 4 layers and 2 scenarios with 3 total layers. This was part of the project. So they have to optimize, and the reason why I said this is because people were cheating. They were like one full depth payment and call it a day, right? It's like simple, easy. That's when I had to I had to use some constraint. So they do it in Excel and they develop a program, then the macros and everything. You guys can do that. And that's the traffic you can calculate. This is to get that UF, the damage, right? That's the. There's another one given to you. This is all right here. A 12-inch unreinforced portal is placed directly on a granular subbase, right? 12 feet and joint brace are 22 feet apart. And you have these properties, modulus of elasticity, right? Remember, I went through some equations I just covered in the textbook. These are the ones I would do corner straps, edge straps, interior straps. You would forget it, right? But most important I make them do is compute the combination of temperature and loading. Remember what I do night time, daytime, when the tension is mapped, that is very critical. That is very important for me to know, like the students understand when the difference is there. Let's look at this. What is the difference between tie bar and dowel bars? Tie bars happen parallel, so tie bars, yeah, they happen parallel, this is the graphic, they happen parallel to they tie the longitudinal joints. And if there's a joint here, another joint, then you have dowels here. Right? Or transfer, yeah. So between
Load transfer.
load transfer, right. This is the tie in this, just the tie bar. What is the difference? What is the difference between JPCP has no reinforcement in there. They may have about maybe 5 to 15 feet. JRCP has the wire fabric for temperature, and you have dowel bars. And CRCP, remember I talked about they form cracks on their own. They can have their own cracks. So that's what. Here are some of the designs you can do. See, I did not know that people would have access to this book on art, right? I did not have a sense of whether they can do the whole problem, but okay, let's do this more. Well, true or false, they are the fun ones. Let's do all of these and then we will see. First one. Anybody? So you have your this JPCP, you have the length of the slab is so small, right? Your delta L is less than 0.05 inches. Remember that equation I wrote down? Delta L is equal to CL alpha delta T plus epsilon, right? Right? And if this is less than 0.45 inches, you do not need dowel bars, right? Okay, great. So that is what this is, right? So this is what this ensures that your slab length is so small that you do not need a dowel bar. Next one. So one side should not be bonded, other side should be bonded to allow for free, right? So now, so one side should be bonded to guard with, other side should be free motion, otherwise you will have significant stress develop, right? Or next one. The word only is a trick, right? When I say only, that means is there any other factor I missed? You see what I'm saying? So you can see where I'm going. Only on the thickness of the slab. So if you remember stress ratio factor, everybody with me? Effective subgrade reaction, right? What else? Something else too. There were multiple tables for stress ratio factor. Depends on whether there is shoulder or no shoulders. Right? There was stress ratio factor with shoulder, no shoulder, tie bars or no tie bars. So everyone is there. So it also depends on other factors whether there is a presence of shoulder or no shoulder. Correct? And that is a different table. Does that make sense? So that only is always a trick. Like, okay, they are going to miss something. If I don't put only, then this is still this is also a right answer if you understand what I'm saying. So my students have to know all the factors. They can't miss any. That's why we want only. Next one. The alarm is depend on edge and joint conditions. So that is true. It depends both on the edge and joint condition. Next one. Maximum reinforcement criteria in CRCP is reduced cost. I covered this 2 days back. Maximum reinforcement in CRCP is to reduce cost. What happens when you have very dense reinforcement? What happens in
having so many cracks.
Yeah, it will cause punch outs, right? Yes, it will cause punch outs. In CRCP, you have, if I provide reinforcement very, right, and if I increase it too much, right, then the cracks are going to form. And then cracks are going to go like this, and it's going to bridge, and it's going to come out. The crack width is going to be small because each of the slab size is small, but they eventually bridge. It's not the cost issue, it will cause punch outs, and that's the serious issue. Next one. Yes, no? Which one? It's true. It's true. If you have a if you have a saturated subgrade, it's very uneconomical, right? Your radius of curvature is going to be very narrow. The stresses are going to be very high, right? Because it's going to be very weak subgrade, and therefore you will end up making it very thick, right? But it's very uneconomical. In jointed plane concrete, where am I? Thicker the slab is less likely it needs dowels. Yes, no? It's true, right? So you will have less bearing stresses. So steel reinforcement is primarily for transfer of joints or for expansion and contraction in temperature. Steel fabric. Transfer of joint is only one, dowels, nothing else. So the answer is incorrect because this steel reinforcement is happening in the middle of the slab only for temperature, expansion and contraction. Make sense? Next one. List 4 material properties of concrete that is accounted for design of slab or reinforcement. We just went through them. Can you list to me 4 more properties of concrete? Compressive strength, modulus of rupture, same thing. Modulus of rupture is one more. Need a couple more. You have bond strength with the steel and 4 material properties. Modulus of elasticity. Modulus of elasticity is what you need, right? And there's something related to reinforcement which I have not covered. So there's compressive strength, modulus of elasticity, flexural strength, and there's one more. Coefficient of thermal contract. That's a great one. Coefficient of thermal contract. That's excellent. Why are edge conditions important in fatigue design? Yeah, and the stresses are going to be very high, right? Illustrate by figure to show position and time loading effects of performance. That means I make them draw figure where the edge, and the center explained and so on. All right, let's answer. So you can do that. We already covered that. It's in the slides as well. Yes or no? So these are not jointed CRCP. JRCP is always dominant. KPCP may or may not have dowels, right? And yes or no level. Level of reinforcement, none, light and heavy, right? Does that make sense? And we can next one.
So include following is flexural strength and Poisson's ratio and modulus of elasticity.
Poisson's ratio is also one of them. That is excellent as well. I missed that. Good call. Awesome. All right. How does the depth to rigid foundation, think with me here. How does depth to rigid foundation and coefficient of thermal contraction of concrete affect the design slab thickness and AASHTO method? Understand the question, right? If I increase or decrease the depth to rigid foundation, just that, everything else be constant, what will happen to the slab thickness? My depth to rigid foundation decreases. That means my rigid foundation gets closer and closer to the pavement. Will my thickness increase or decrease? You have better support and therefore it will decrease. Alright? Everybody understand that? You should be able to understand from all the tables how it correlates. Next, if your coefficient of thermal contraction increases or decreases, what happens to design thickness? Yeah, so it will increase your thickness will increase, right? Because you get more stresses, right? Next one. But it's more on the reinforcement side as well. All right, next one. Which two criteria is considered for thickness design of cornice using PCA method? Which two criteria is considered? We just went through this. Fatigue analysis and erosion analysis. That's absolutely correct. Fatigue is purely due to stress factor, right? Stress over SP. If that is closer, you'll have more, and erosion is completely due to pumping. Which one of them must be satisfied with the safe design? Both, right? Both, right? This is another trick question, right? Which one of them? Both have to be satisfied, right? Both, you asked me that question. Both have to be less than 100, not only one, right? Next one, which mechanical responses are critical to each of these criteria? So one is the stress, one is the deformation. One causes deformation. The erosion factor is completely related. All right. Explain the four-step process of calculating a single effective from resilient modulus of grid over subbase of load modulus. That is exactly the charts, the three charts, right? Accounting for thickness of the subbase, modulus of subbase, and then you have depth to rigid shallow foundation, and then finally loss of support. That's it. Anything else I'm missing? Any question on that? I have some fun questions. Some of them are put together. And, any like I did not do any math problems, but that will have to that takes up a lot of time. But any questions on this? Any other questions about any of this? I'm trying to look at any more problems that I can give you. Any concept problem that I can give you. Anything else you want me to cover? Let's see what you're doing tomorrow. I can't believe you have covered 100. At least some of those I covered with the textbook. Oh, this is the fun one. I'll cover that tomorrow. Okay. Any other questions? Yes, please. Yes. Yes, please. What's your question?
For mechanistic empirical,
Yeah.
just you explain the asphalt institute or you explain other methods like NBDG or
Tomorrow. Tomorrow. Tomorrow I'll explain payment ME design.
Okay.
Yeah, tomorrow I'll do payment ME design. These are the slides for tomorrow, and I'll explain payment ME design tomorrow. But we did PCA, which is also the payment ME, right? I'm sorry, mechanistic impediment, PCA. But tomorrow I'm going to explain payment ME design. And not many slides, but I'll cover it. Questions? Any other questions? Any other queries from anybody? I think that's. We need to call.
That's one question apart from the curriculum, sir.
Yeah.
Sir, how often do you visit India, sir?
I try to visit often. Meet my mom in Bombay. So I try to come once a year. And whenever I come, I try to do talks, but now I've reduced it because I go to Bombay. I try to spend. This time I came August 4th. I was in Bombay and then I came here. But yeah,
Sir, do you know English, sir?
very well. I came here after 21 years. So
After 21 years?
yeah, I got my bachelor from University of Mumbai.
I can see.
Huh?
I can check your email.
Yes. हाँ, हिंदी बराबर समझते हैं बोलते हैं सब कुछ
Yes, sir.
yeah. हिंदी गुजराती little bit of Marathi Urdu yeah. I think we covered